Hi all, my name is Malcolm Bernard and I'm a PhD student at University of North Carolina's Institute of Marine Sciences here in Eastern North Carolina. Welcome to our second seminar in Eastern North Carolina section of the American Chemical Society Diversity in the Chemical Sciences Seminar Series, funded by a local section sustainability programming grant from the American Chemical Society Committee on Environmental Improvement. Before I introduce our incredible speaker for today, I want to talk about a few Zoom seminar housekeeping items. If you have questions, please type your questions in the Q&A portion below, and they'll be answered when Keisha is able to see them or at the end of the seminar. Additionally, this seminar is being recorded and will be available after the seminar on the Eastern North Carolina ACS YouTube channel. I will share a link to the YouTube channel in the chat at the conclusion of the introduction. Hope you all will have a chance to check it out. Without any further ado, it is a great honor to introduce today's seminar speaker, Dr. Keisha McDowell, who is a principal investigator with DuPont Nutrition and Biosciences Global Engineering Technology Division. Her technical expertise is in moisture characterization and control for dewatering and drying processes and dried products. Dr. McDowell has more than 20 years of experience in industrial engineering research towards product and process commercialization, applications development, technical service, and manufacturing consulting. She has demonstrated experience in laboratory, pilot, and commercial scale operations involving food ingredients, enzymes, bioactive cultures, natural and synthetic polymers, and traditional chemicals. She received a Bachelor of Science and a PhD in chemical engineering from the University of Maryland and the University of Florida, respectively. She is a senior member of the American Institute of Chemical Engineers, has served as an adjunct faculty in the Department of Chemistry at Morgan State University in Baltimore for the last 8 years, and is a frequent guest lecturer at the University of Delaware in Newark. Today, Dr. McDowell will be talking with us about effect of dehydration and particle formation processes on the water vapor sorption characteristics of skim milk powders. Please welcome our seminar speaker, Dr. Keisha McDowell.
Thank you, Malcolm. I appreciate that introduction. Thank you for the invitation and for welcoming me to speak to your section this afternoon. I'm going to start sharing my screen, and please let me know if anything I'm doing is not working. So let me do that. Okay. Am I sharing properly? Everyone can see my chart?
Yes.
Okay, good. So again, thank you so much for the introduction and thank you for the opportunity to speak this afternoon. I do appreciate it. Again, I will be talking about dehydration and particle formation processes of moisture and water vapor absorption characteristics of skim milk. You might wonder why I'm talking about skim milk. I'll say a little bit more about that when I get to that portion of the talk, when I talk about materials and methods. But skim milk has a lot of interesting characteristics that are ripe for study. Also, dried non-fat milk powders are a typical food ingredient used in many formulation. And so its properties in terms of understanding basic analytical and characterization techniques is very useful. And again, the material itself in formulation of various food ingredient systems is quite fruitful. So skim milk powders are a really nice model system to use for a number of different types of study and characterization behaviors. I'm going to talk a little bit about today what you see here in the outline, particle formation via drying. So I'll talk a little bit about that to give you some background and grounding on the types of drying technologies that I'll be discussing toward making dried skim milk powders. Then I'll move into talking about moisture and moisture absorption characterization. There's a couple of different ways that we tend to look at moisture analyses. And I'll speak a little bit about that in terms of which can be better or best in different situations. Then I'll go into some specifics regarding some comparative analyses between powders made from different forms, and give the materials and methods on those, as well as the experimental results. And then I'll conclude with talking a little bit about the results that we've seen, how they can be used toward different types of analyses in terms of understanding and defining appropriate storage conditions, packaging, etc. And then I'll end with some acknowledgements, because certainly I didn't do all of this all by myself, and I had some help from a number of my colleagues who I'll acknowledge today. And from the participant list, I see a couple of my colleagues in the attendees, so I appreciate them attending as well. First, I want to just give you a little introduction about myself. Malcolm read a very nice introduction, but I want to say a little bit that I put this slide in because I'm thinking of the young lady who was the Youth Poet Laureate at the inauguration ceremony yesterday. And I thought she was such a wonderful example in terms of her poise, in terms of her grace, in terms of her articulation, and just her writing ability in providing such a thoughtful word for the day. And my daughter, who is in the 9th grade, had an American government assignment for her class to watch the inauguration. And I was so pleased to see this young lady, Amanda Gorman is her name, provide such an inspirational message as part of the ceremonies. And it reminded me how important representation is for our young people. And it made me think about when I was a young person, my daughter's age, or maybe younger, probably most likely younger, even though I'm going to show my age a bit by making this comment. I used to love the show The Jeffersons. I used to love that show. And Lionel Jefferson, who was the son, he was an electrical engineer. And that was my first introduction to engineering, was Lionel Jefferson on The Jeffersons. And it made me think about being an engineer. And this poster, I want to be an engineer just like my mom. My mom's not an engineer, but Lionel Jefferson was on the wall in the engineering department at the University of Maryland. And so it just reminded me, seeing the young lady yesterday reminded me of how important representation is and how important it is to make sure we have people who look different, being an example for others to follow. So I'm going to talk just a little bit about my background, just so you know where I came from. The most important thing in the world to me is my family, and everything I do is really for them. As you know, I am a chemical engineer by training, so many aspects that I'm going to speak to are going to come from an engineering process development perspective. I am a full-time engineer at DuPont, but I do some teaching on the side. I get some of my thrills from that, in that I find that the students give me a lot of inspiration to come back and try different things in the lab that I may have been thinking of. And then I find that the time that I spend teaching also helps inspire me with, different things that I can explore in my full-time job at DuPont. Students tend to ask very, very good questions, many of which I don't have the answers to, and it makes me want to go back to work at DuPont and try to explore more, try to understand more so that I can provide something better for the business. I do like working in the lab. I do like doing laboratory experiments, and I really like digging deep into basic data and really understanding the whys and hows of what's happening. So I work at the experimental station in Wilmington, Delaware, not Wilmington, North Carolina. I know I'm talking to some North Carolinians, so not in North Carolina, but in Wilmington, Delaware. And this is an aerial shot of the experimental station. It looks and feels very much like a college campus. I remember when I started there in blah, 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 many years ago. So in 1999, literally in 1999, I started at DuPont at the experimental station. And many people at that time would refer to it as the campus. I'm going to the campus, or I'm going to be on campus tomorrow. So, I mean, it really has that look and feel of a college campus. I think part of that gives us a lot of time to think about the exploration of what we're doing in terms of some basic development, some basic research type aspects of our work. So I've been there for 20 years off and on, and it has provided a fruitful area for research for me. When we talk about drying, drying is area of technology that can be deceptively simple. The definition of drying from Perry's Chemical Engineer's Handbook talks about thermal dries in terms of vaporizing a liquid from a solid. So when we talk about drying as a unit operation, we're talking about heating and then vaporizing, so a phase change. So drying can be used for a whole manner of different things in a sequence of unit operations in a manufacturing process, to prepare ingredients, to reduce shipping costs, extend shelf life. All those different kinds of things can be one of the reasons why drying is being employed in a unit operation. A lot of energy is involved in drying. One of my colleagues tends to say the best dryer is no dryer, because of the amount of energy and explanation that it requires to get to a good solution for a product. But one of the things I want to leave you with is, again, when you're doing a drying operation, drying is simultaneous heat and mass transfer. Both of those things are happening at the same time. Again, it's deceptively simple because many people have dryers in their home. They have a microwave, they have a clothes dryer or something like that. So drying appears to be something that we know and or understand. But although it is simple in terms of its concept, externally simple in terms of its concept, many of the aspects of drying cannot be fully explained mathematically, and there must be some experimentation in order to further understand it. Typically, when we're classifying dryers, we can do it in a variety of different ways. I like this way in which this was put together, because it shows that you can look at a variety of different ways to do the classification. It doesn't have to be just one mode that you may be looking at. The modes that I'm going to talk about today are going to be in terms of the heat transfer mode. So in terms of the four particle formation processes that I'm going to talk about today, it's going to be looking at spray drying and freeze drying. And as you can see, they have very different heat transfer modes. I'll talk more about it when I get to that point of the talk, but freeze drying is essentially a conductive drying methodology that is not based on vaporization. Actually, sublimation is the key driving mechanism for freeze drying. And spray drying is a convective drying mechanism that still does use vaporization, the liquid to vapor transformation as the effective drying means. But again, they have different heat transfer modes, as well as different contact modes between the solid and the heat transfer means. But even though you can classify dryers a variety of different ways, when you're selecting a dryer, usually the first consideration is the form of the feed material that you're going to use. So there's some basic drying processes that can be used when you have a feed material that is in the form of a liquid. So when you want to go from something that is discernibly liquid, not just something that's wet, but something that you could want to classify as a liquid, when you're talking solid, liquid, vapor, is this a liquid? If you're going to go from liquid to something that is discernibly solid, there's a few different methods that you would consider. Here's three main ones that are listed here. One of them is drum drying. I'm not going to talk about drum drying in any detail in this talk, but just want to bring it up because skim milk is also made via drum drying processes as well. Some people are familiar with drum drying. I put a picture there so that you can get a feel for what that is. A lot of food flakes are made via drum drying. So like oatmeal is made via drum drying in some cases. Oatmeal flakes, instant oatmeal flakes. Fish food that you see, those little flakes are also made by drum drying too, where the product comes off, starts as a liquid, but ends as a dried solid in the form of a flake or a small or large coarse powder. Freeze drying and spray drying are the main drying mechanisms I'm going to talk about as part of this talk. Again, as I mentioned, skim milk is made via drum drying in some cases, but spray drying and secondarily freeze drying are the primary mechanisms by which skim milk powder or milk powders in general are made from liquid to solid industrially. Freeze drying is a dehydration process where you remove water via sublimation at low pressure. So unlike the definition of drying in Perry's 8, sublimation is the primary phase change that occurs in freeze drying. In spray drying, you take, again, a liquid feed to a powder in one single processing step. As long as that liquid feed is sprayable and pumpable, you can most likely spray dry it. Some materials can have very different rheologies that may make them unsuitable for spray drying. Usually it's the rheological profile in terms of you wouldn't want something that would be shear thickening, that would be an issue in spray drying. But again, you can have a variety of different types of liquids, solutions, suspensions, emulsions. Again, if I can pump it and spray it, I may be able to spray dry it. So the advantage of that for spray drying for many people is the scale. So that becomes quite an advantageous process for a number of applications where you want to go directly from a liquid to a solid. So I see one question is, what size do you characterize as a fine powder? So a fine powder would be something that I would characterize as a flowable and not macroscopic. So I wouldn't, something smaller than a few hundred microns, probably in the range of 500 to 800 microns might be more coarse, what I would call a coarse powder. But something small, small and flowable where you don't discernibly see the individual particulates. And so I think something that falls just outside of the visual distinction of the individual particles is what I would call a fine powder. I'm not sure how to turn the question off once I've answered it. I think, okay. Okay, there we go. Okay, next slide. Next slide. Okay, just some more information about what spray drying is. Some people who do spray drying on a laboratory scale may recognize the size of the unit that you see there on the left. This is a small benchtop size spray dryer where the main drying chamber is actually here, just to the left. This is the cyclone separator, and this is the small collection vessel, which might be a few hundred milliliters, maybe a liter in size. And spray drying can be as large as what you see here on the right. You can sometimes see these large industrial spray dryers from the interstate highway when you're driving. So spray drying can have a large range in terms of scale. And that large scale is one of the things that makes spray drying advantageous. Again, just to quickly summarize what the spray drying process looks like. You have a pumpable feed and then a gas supply that will contact that feed. The feed goes through some atomization means. There are a number of different ways in which you can atomize the liquid feed into small droplets. Those small droplets contact with the gas. I'm showing the gas is entering at the top of the spray dryer, that is rather at the same position as the feed, but spray dryers can be configured in different ways where the gas flow could enter tangential to the droplet formation. It could also enter counter current, say from the bottom, for example, to the droplet feed as well. But essentially you have your pumpable feed, it's atomized through some means, it's in contact with a hot gas. That hot gas against those small droplets results in a flash of evaporative liquid from the particles. Those particles are then separated from the gas flow in a cyclone separator, or you can have a baghouse or some other type of solid gas separation means. The gas exhaust is removed and the dry powder is collected. So again, you can go from a liquid feed to a dry powder in one process step. Freeze drying, on the other hand, works very differently. As I mentioned, freeze drying uses sublimation as the primary heat transfer mechanism. And some people in labs, just as I showed the lab scale spray dryer, some people will recognize this small manifold sized freeze dryer, excuse me. So these little bottles, these little flasks attached to this manifold is one of the smallest size freeze dryers you might see in a laboratory setting. Freeze drying operates by first cooling your feed to a super low temperature, then you drop your pressure, then you basically have a heating at low temperature. So you still are applying heat, but the heat is at such low temperature, and you're at a point on the phase diagram of water where you don't have the liquid to vapor transition as with spray drying. You have a solid to vapor transmission through the sublimation means. Again, this is very, very small scale. An industrial scale freeze drying, this is usually what you will see, where you will have multiple trays of material sitting on different trays. Again, you'll have bulk, liquid, or pellets, or flakes, or sometimes vegetables or fruits or whatever, sitting on different trays. Those trays are heated, and that conduction of the heat element through the tray to the product effectuates the freeze drying. Just as I showed a schematic for the spray drying, I'm showing one for freeze drying here. And this shows a tray style freeze drying scheme. So again, industrially, most things industrially are dried in trays via freeze drying. So again, you would have a shelf. And as I showed on the previous slide, you could have multiple shelves. You could have 20 or 30 shelves on some large freeze dryer. And on each one of those shelves, you would have maybe multiple trays. In a benchtop lab scale tray freeze dryer, you may only have one shelf, one tray, two shelf, two trays, that kind of thing. But industrially, you could have 4, 5, 100 trays on a shelf. Again, the shelf is heated through some type of cooling liquid like ethylene glycol or something like that. The shelf is heated, and then the freeze drying occurs on the tray, actually from the top down. So as the heat is being applied to the bottom of the tray, the sublimed ice actually moves from the tray, where you have a differential in pressure from the tray, the vapor pressure you'll be experiencing there, to a fixed vapor pressure from a condenser. So you actually have a transfer of solid water, which was frozen in the tray, to vapor in the condenser space, so in the chamber space rather, and then it will collect at the condenser as solid once again. So again, you have this solid transformation, solid to gas transformation that happens via freeze drying. If you look at the phase diagram of water, where you have solid, liquid, and vapor, you can see the schematic of how freeze drying occurs. So for example, if you had a material at normal temperature and atmospheric pressure, it might be sitting around here at 20 degrees Celsius at normal pressure. And then if I wanted to use normal thermal drying, I would just increase the temperature until the liquid water vaporizes, goes from solid to vapor. However, for freeze drying, I would first reduce the temperature. So say, for example, to about minus 40 C or so. I would reduce the temperature, then I would reduce the pressure to a point where I could further increase the temperature again to effectuate a solid vapor transition. So again, this is the mechanism, this three-step process is the mechanism for freeze drying, whereas this process across the liquid vapor line is the process for thermal evaporative drying, like spray drying. So next I want to move into moisture and moisture absorption characterization. And first I want to talk a little bit about what are moisture contents that we're going to talk about. So many people are familiar with a typical moisture content measurement. That is how much water is present in the material that I'm dealing with. Now, I'm not going to get into different methods of moisture content measurement. I'm not going to talk about loss on drying versus Cole-Fisher or something like that. But suffice it to say, we can be agreed that there are different methods to measure essentially the amount of water that might be present in a system. Contrast that with water activity. Water activity is not a measure of amount of water, although I'll sometimes hear people say that in terms of thinking of bound versus unbound moisture. So I'm not going to get into that conversation either. But suffice it to say, water activity is not a measure of the amount of water present. It is a measure of the energy status of the water present. And so the amount of water present does have an impact on the water activity and the energy status of the water present, but they're two very different things. And depending on the nature of the materials that you're dealing with, the water activity measurement can be much more informative, much more predictive of the types of behaviors that a material might exhibit than the actual amount of water that's present. I'm using some terms here. EMC is equilibrium moisture content. You'll see that in a little bit. versus ERH, which is the equilibrium relative humidity. And I'll say more about that in the next slide. So what is water activity? As I mentioned, water activity is a measure of the energy status of water that is present. So you'll have some quantity of water present in your system. It will have a certain energy status that will then affect how that material will behave in different types of situations, for example. And so water activity is essentially the equilibrium vapor pressure of water in that material divided by the equilibrium vapor pressure of pure water at the same temperature. So see, because I've talked about vapor pressure, that means I have to talk about temperature too. So when we measure water activity has to be measured at a specific temperature. Just as vapor pressure is a function of temperature, water activity is a function of temperature as well. So when I'm talking about water activity, I'm talking about a functional relationship that has temperature as an independent variable. So water activity is related to equilibrium relative humidity. So the actual humidity that you have in the environment around you is related to water activity. If I take my sample, if I have a sample of material and I set it in a certain environment that has a fixed temperature and a fixed humidity, eventually the water activity of that sample will equal the humidity of the space around that sample. There'll be a vapor equilibrium between molecules evaporating and condensing back into the sample and back and forth from the sample and headspace. So water activity is typically shown as a decimal, whereas relative humidity is shown as a percentage. But essentially, because the water present in that sample has some energy status, there is now a availability of that water to participate in different types of reactions: chemical, microbial, physical, and potentially others. And so even though people will sometimes think, well, the water is more active, so that means it's not as tightly bound to the product. And that's really not a proper characterization to talk about bound versus unbound water in terms of water activity. Water activity is really not a measure of bound versus unbound either. It is the availability of the water to be, engaged if that material is in a situation where it could potentially react chemically, microbially, or physically with something else in its surrounding space. Because water activity is the primary criteria by which we characterize biological-based systems, because water is essential for life, there are a number of different characterizations that have been defined and have been utilized throughout the years. So I'm showing here a chart of 5 different characterizations of a moisture absorption isotherm. And what this is the relationship between moisture content and water activity, or equilibrium relative humidity. As I mentioned before, moisture content is the measure of the content of water that's present, whereas water activity is a measure of the energy status. And I mentioned earlier that moisture content will have an impact on water activity, and you can see that via the relationships I'm showing on screen right now. So a concept known as the moisture absorption isotherm is the relationship between moisture content and water activity. Again, water activity can also be related directly through just decimal to percentage conversion to the equilibrium relative humidity. Type 1, 2, and 3 isotherms are very, very common. Type 1 isotherms are very common for materials that can hold a lot of water at low humidity levels. Zeolites, anti-caking agents, those types of things that can absorb a lot of water at low humidities are very common type 1 type materials. Whereas type 2 and type 3 materials, you see very common in food systems. Why do you see that? Well, in many food systems, you have a formulation. So your food may have salt in it, it may have sugar in it, it may have skim milk powder in it, it has a variety of different things in it. And so because of that, you can see this composite sigmoid shape, that's a type 2. If it's heavily weighted with salts or sugars, you might see this type 3 material, that's type 3 isotherm, that's very common with sugars. Type 4s and type 5s are available in the world, but not as common in type 2 and type 3. A type 4 is very similar to a type 3. You just have an asymptotic leveling off of the equilibrium moisture content at high humidity. Similarly, for type 5, again, you have an asymptotic leveling off of the equilibrium moisture content at high humidity. Okay. So there are a few different ways where you can measure moisture absorption isotherms, and we use all of these different techniques in my lab at the experimental station. You can use some very old school, what I call old school, the old school salt methods, where you have salt solutions and desiccators, and you allow your sample to come into equilibrium with the humidity of the environment. So different salt solutions will generate different equilibrium relative humidities in the headspace. So for example, if I take a solution of 13.41 molar lithium chloride and I put it in a enclosed chamber at a fixed temperature, the equilibrium headspace of that chamber will be 25% RH. And there's a number of different salt solutions that function that way. 6.0 molar sodium chloride has an equilibrium relative humidity of 0.76 or 76% humidity. So there are a number of different things that function that way that can give you a fixed a humidity environment that you can then use to generate a moisture absorption isotherm. So if you wanted to use a traditional old school method, what I call the salt solution method, you could put a variety of different desiccators with different salt solutions in them, put your sample in the salt solution, allow your multiple samples at these multiple humidities to come to equilibrium, and you can use that moisture content and humidity data pair as one point on your isotherm. Nowadays, we have some automated methods that can do that as well. And those are the ones that are squared in the blue boxes that you see on screen. We've used all three of these methods. The one that we use most often nowadays is the one at the bottom center, which is actually made by Aqualab. So it's Aqualab Dynamic Vapor Absorption Unit. It also does a specific type of isotherm that Aqualab calls a dynamic dew point isotherm, but I'm not going to talk about that today. But traditional DVS, that was pioneered by Surface Measurement Systems, which is the company that makes the equipment in the top center. Essentially, instead of having to have multiple desiccators at different humidities to generate each data point, you can program the instrument to do a step through the humidity levels that are of interest to you. So you could load your sample, say, for example, at its fixed starting moisture content and water activity, and program the instrument to move to the next humidity level that's of interest. So say 40% RH. Allow the sample to come into the equilibrium with that humidity environment, then program the instrument to move to the next humidity level, say 60% RH. And this test can run automated for you, thereby generating a moisture content, water activity, or humidity data pair as a point on the moisture absorption isotherm. So now let me talk a little bit about the materials and methods that we use in terms of characterizing these dried powders via the moisture absorption isotherm methods. So we use skim milk. So skim milk is a very nice model system that we can use because, again, as I mentioned, it is quite ubiquitous in food formulation. It also has a number of different properties given its number of different properties due to the lactose content, for example, that make it very interesting for study. But as I'm showing here, you see spray drying has been around since the 1870s. And you see as early as 1921, there was an article published here by R.S. Fleming about spray drying of skim milk. So spray drying of skim milk has been around over 100 years. And in the bottom right, I'm showing some commercially prepared cakes of skim milk that have been freeze dried. So you can see that in the freeze dryer, the skim milk is coming out as a friable cake. So you take this out of the freeze dryer from your trays. It will be in a cake form, if you will, kind of like a, how should I say, what's the thing? The rice cake, like a rice cake that you can easily break apart. Sometimes after freeze dried cakes are produced, they go through a milling process to generate a particle size that may be of particular interest to how the powder will be used late down the road. But again, it's very common in industrial practice to either spray dry, freeze dry skim milk. And so I'm going to talk a little bit more about that. In the labs that we have at the experimental station, we have 2 spray dryers that we've used very often. We have the one that you see on the middle, which is a very small laboratory size spray dryer, similar to the one I showed in the picture earlier in the talk, where you can process about a half a liter to a liter of liquid feed at a time and generate several grams of powder that you might want to use for evaluation purposes. On the left-hand side, I have to give a shout out to my coworker, Steve. Steve is almost famous because I got his permission to show this picture because having a person in the picture really gives you an idea of the scale of the dryer. So the dryer, again, on the left is a modified mobile miner. So those of you who know about spray drying may be familiar with a GEA mobile miner sized spray dryer. This unit can process several kgs of liquid at a time and produce several kgs of powder. So there's about a 10x difference in material, or excuse me, 10 to 100x difference in powder production between the 2 sizes. We've used both sizes of this equipment to produce spray dried powders of skim milk and other things in order to evaluate the effectiveness of the process, the characteristics of the characteristics and properties of the produced powder, etc. Some of the process variables that are important are listed on the right in terms of how you can effectuate different types of characteristics in the powder that you're going to produce. And from a freeze drying perspective, we used our lab scale freeze dryer. Our lab scale freeze dryer, again, this is Steve's hands that you see to give you an idea of the scale of the lab scale freeze dryer. This is a benchtop unit as well. And we use this to freeze dry, again, in trays to make cakes of cakes of freeze dried powder, milk powder, for us to do further evaluation. Again, the cycle parameters for freeze drying were shown on the right there in terms of temperature, pressure, time, and drying rate. So the materials, again, that we used for this analysis were fat-free or skim milk that we purchased from a local grocery store. The milk was 89% water, so only 11% solids, which includes, lactose, proteins, variety of different things that are the particulates in skim milk, but no fat. The fat would present a particular challenge in terms of stickiness and what have you in the spray dryer. So that's why we don't use fat milk in the processes that we're running. You see the conditions here that were listed for the spray drying and freeze drying processes. And then finally, you see that the product collected for spray drying, the spray dry powder was about 6% moisture, whereas the freeze dry powder was about 3%. You see the water activity, it was about 3x for the spray dry powder. It's more moisture content and higher water activity. We talked about the relationship between the two already, but you see a little bit lower water activity for the freeze dry powder. And then there's analysis of the particles that were produced. The spray dried particles were really fine at around 7 to 10 micron, whereas the D50 of the freeze dried powder that was produced, again, we generated a friable cake that was easily broke apart into about 40 to 50 micron sized particles. I would still consider that fine particles. Here's a summary of the particle size distributions, just to give you a sense of what we're talking about again here. Again, with spray drying, we're producing fine particles in a spray, again, a spray atomized particles that we're producing. So you get individual particles as part of the product. Whereas freeze-dried particles, because we are freezing the material in a layer on a tray, you actually produce somewhat of a scaffold structure. That is, the frozen ice acts as a scaffold to maintain the structure of that liquid that forms a cake on the tray in the freeze dryer. So as you sublime, you remove away the scaffold while maintaining the structure. So the ice is being removed, but the porous structure of that cake remains. That provides some structural formation toward different properties that you'll see down the line. And here you're seeing some SEMs of the different particles that were produced. The spray drying process will generally produce a rounded shape of particle. In the case of these milk powders, which you'll see with a number of other powders as well, you will see concavities along the outer surface of the particle. So the morphology will be a rounded particle with some concavity divots on the surface. These concavities result because of the rapid drying that happens through spray drying, and also because the moisture content of the liquid feed is so high. There's such a rapid evaporation happening at the surface. Whereas again, because the freeze-dried particles are produced in a layer where their structure is maintained, even though the ice scaffold is being removed, you get a nice smooth layer of surface that's being produced. So once we took a look at the dried particles themselves, we were then in a position to evaluate the moisture absorption isotherm, which is the relationship between the equilibrium moisture content and the equilibrium relative humidity, or the isotherm. I'm on the data here, you see that you have a difference in temperature. So I mentioned earlier that the equilibrium relative humidity and the water activity are both a function of temperature. So I wanted to look at the effective temperature. You see a slight difference in temperature as a function of water activity, and that's pretty typical, that as temperature increases, equilibrium moisture content will decrease. That's pretty typical that you'll see for many materials in the literature. Sometimes you'll see that as these curves move to higher equilibrium relative humidity, you may see a crossover, so that maybe at high relative humidity, the higher temperature curve may be on the top this time instead of on the bottom, through an inflection point. In terms of comparing the spray dried and the freeze dried powders, again, you see that same type of type 2 sigmoid shape that we saw previously, and in the characterization of the isotherm forms that I showed earlier in the chart. One thing that we did not see with our powders was that we did not see this discontinuity. We took the time to purchase some commercial granulated milk from the grocery store to see if we could see this discontinuity. One of the things that's well published in milk isotherms of skim milk, is a discontinuity in the moisture absorption isotherm due to lactose crystallization. We did not see that in the original powders that we spray dried, and most likely because we know where the crystallization is supposed to happen, it's because our data is not fine enough that we didn't see it in the smaller powders that were produced via spray or freeze drying. But in the commercial granulated isotherms, we were able to see that discontinuity that is well published due to lactose crystallization. So when we went to model the moisture absorption isotherms, we chose two different models that are also quite common for food systems and a number of composite formulation systems in the food industry. The BET model of BET surface area fame, so it's the same researchers that generated the concept of the BET surface area. There's a linear isotherm model that we can use that takes into account the water activity, the equilibrium moisture content, and has two parameters, this M0 and C that I'll talk about on the next slide. A more popular isotherm, or just as popular, but more of an effective range isotherm, is this GAB model. And this GAB model also takes into account both data of the equilibrium moisture content and water activity, but there are three parameters. And both of these models are useful because not only have they been shown to fit a number of different food systems, but they both are based on the same principle in terms of monolayer moisture coverage of absorbed water molecules, but have a physical significance. The individual parameters have a physical significance in the phenomena that you see with the materials. The M sub naught is the monolayer moisture content. That is the amount of water that would absorb onto a surface to generate just a monolayer of water. And then you have the energy constant, which is related to the heat absorption of the waters that are absorbing onto the surface. And then K is a fitting parameter that's used for correcting absorb layers with respect to bulk moistures when you really get into higher layers, into higher values of the equilibrium relative humidity. So by using the GAB model, we were able to very easily model the moisture absorption behaviors of the skim milk powders through that we've generated via spray drying and freeze drying. And we also did some modeling for the commercial granulated sugars as well. If you take a look at the model parameters from the Guggenheim-Anderson-DeBoer model, again at 20C, I have them summarized here for you. So from the modeling from the previous slide, here you see the different model parameters. One of the things that you'll notice is that the freeze-dried skim milk has the lowest absorption energy. It has the lowest energy constant with the lowest energy absorption behavior, which means that the ability of water to absorb onto this surface is much easier because there's a lower energy barrier. Similarly, you can see that the freeze-dried products also have the highest monolayer moisture content. With easier absorption of water, you have more opportunity for the water to absorb, and so therefore this material would be considered more hydrophilic than the other two. Lastly, I want to summarize with talking a little bit about packaging considerations. Whenever we are dealing with food systems, we have to be concerned about how those materials will interact with the environment around them, because we know that just as water is essential to life, we also have the effect of water has on living materials, the potential for bacterial growth, etc. So one of the things we want to make sure that we understand is appropriate packaging. All packaging materials will have some type of permeation on how can the room environment filter and or seep in across the barrier of the package into the product. And one of the ways in which we characterize the ability of the package to permeate moisture, humidity into the product containing that package is by a concept called the water vapor transmission rate. There are other things that you can consider in terms of permeation, like an oxygen permeation rate, a nitrogen permeation rate. But for these purposes, I'm going to be talking about water vapor transmission rate, or WVTR. Packages can have different WVTR and be affected different ways by their environment as well. Something like a foil package is essentially zero WVTR, zero permeability. And you can see there's some data that I pulled from the literature around reported WVTR values for aluminum foil. For different types of plastics, you will see also different water vapor transmission rates through a packaging film. And of course, as you might expect, as I increase the thickness of that film, thereby increasing the cost, you decrease the water vapor transmission rate, that is the permeability of that film to environmental factors like temperature and or humidity. Essentially, packages like glass or metals would be considered no permeability, but permeability to water vapor would increase as you go to paper, plastics, then paper. And of course, this plastics consideration, just like with this low density polyethylene or high density polyethylene, could vary depending on the composite structure. So what you can do is, once you know the moisture absorption behavior of the material that you're studying, you understand how it will change as a function of the equilibrium relative humidity around the material, how the moisture content will change. You have that definition of that behavior through the moisture absorption isotherm. You can use the characteristics of an isotherm to define what an appropriate package and or shelf life would be. So for example, if I took my freeze-dried skim milk powder, I know what the initial moisture content is. That is, I took that from the final moisture content coming out of the freeze dryer. I would define what the equilibrium moisture content is at the external conditions that are of interest to me. So for example, if I want to store my skim milk at 50 degrees C and 50% RH, I would have those definitions. I would also have to define what my critical moisture content is. That is, for example, am I storing this milk in a place where the milk is going to start to smell? So after a certain time or temperature, the moisture will, the milk will start to smell or what have you. the area of the package I'm going to put it in. Am I going to put it in a bottle or a jar? That kind of thing. How much mass I'm going to put in, as well as the thermodynamic considerations of the environment around it. And there's a simple equation that you can use where at the critical moisture content would be related to the shelf life. You could define what the water vapor transmission rate of the package would need to be, and therefore define the package that you would need. For many materials, you would want a full characterization of the moisture absorption isotherm through all the relative humidities under consideration. Depending on where you're going to ship or store your package, you may be able to use the more simplistic linear BET model and just use the slope of the tangent curve, for example, as a fit to defining the package. More complicated models outside of BET or GAB models might require you to do some numerical analysis to characterize a WVTR at each different point. So in conclusion, I want to just show that we did do some moisture absorption behaviors of our skim milk powders produced by both freeze drying and spray drying. And we saw that, oh, I keep clicking. And we saw that both of those showed type 2 sigmoid shape behaviors that are typical of food materials. We saw that the equilibrium moisture content decreased with temperature, as we see very often with food materials, and that the GAB model showed good fit through the full range of the humidity that we studied. The differences in the GAB model fitting parameters could be related to the structural differences we see through the types of particles that we produced via both spray and freeze drying. And one of the things that we might want to look at further is the development of that structure in our freeze drying process, for example, through cryomicroscopy or freeze drying microscopy. Finally, we can use these data to help determine optimal storage conditions, because we now know how the material will perform in different humidity levels. And we can use the isotherm data to define appropriate packaging for materials that are of interest to us. So I want to end with some acknowledgement of my colleagues in DuPont Engineering, as well as some of my colleagues from Corporate Analytical who helped with the SEMs and the particle size distributions, et cetera. Thank you. I'd be happy to answer any additional questions.
Thank you, Keisha. That was great. That took me back to a lot of my dissertation work on surface area measurements. I'd like to first open it up to any attendees that have questions. I think Ryan will unmute you if you're muted. And then I want to, I have about 2.5 questions, but I want to let the, I want to let the attendees have the first opportunity. So please feel free to go ahead.
Okay, so I'm going through the chat, and one question is the odor from the dried milk due to microbial activity? So I'm assuming that you mean if you purchase dried milk from the store and you keep it, and then it starts to go rancid on you. Microbial activity can be a reason for that. It could also be structural breakdown, could also be an issue. It could also be seepage in the package. Again, all packaging will have some permeability. It's just a question of how long it will take for the moisture to seep through that package, moisture and or temperature to seep through that package. I see another comment. Let me make sure I close this one. I see another comment. Nice shout out to Amanda Gorman. Thank you. I really enjoyed her. I really enjoyed her at the inauguration. Thank you so much. I see one more question. Do you have comments, excuse me, do you have any comments on freeze drying of enzymes? The enzyme obviously has to maintain its function. No, unfortunately, I do not have any comment on freeze drying of enzymes. That is outside the scope of this talk.
Any other questions from the attendees? Malcolm, would it be okay if I asked a couple of questions?
Go ahead.
All right. So Keisha, my first question is, with skim milk, you know, it seems to me that it's a pretty homogeneous solution. So how much does skim milk really act as a proxy for other food substances that might vary in, you know, pH or heterogeneity of composition. And
Yeah.
so why is, I guess ultimately, why is skim milk the model substance
Right.
in this case?
Yeah, so that's a really good question. Skim milk, just as when we do particle modeling, we like to have something that's spherical, something that's uniformly distributed. You know, that uniformity does allow us to, you know, really understand some of the basics before we can move to more complex systems. As you mentioned, skim milk is fairly homogeneous. That's why we use skim versus fat or, you know, low fat milk, because the presence of the fat provides a degree of complexity that also makes it more difficult to model. But essentially, because it is homogeneous and it's been very well characterized, it allows us to be able to see structure, you know, structure function, right? And so that's what makes it a really good model system. Also, skim milk, you can see this published in the literature, has been very well used in terms of providing protection to biological systems, in terms of thermal protection, in terms of cryo protection in freeze drying. So reconstituted skim milk is a pretty well-known additive in food systems because of the behavior. Now, some of those mechanisms are not quite elucidated at this point, but because it is so well used in food formulation, you know, understanding completely how it performs is one of our first steps.
Got you. Okay, so its simplicity actually reveals a lot more information than a
Yes.
matrix would. Okay, well, so that leads me to my next question. You mentioned morphology, and you showed the, I don't know if there were micrographs or, are you there?
Yes, I'm here. I'm sorry.
Okay, all right, sorry. You mentioned, I can't remember if there were electron micrographs or high power imaging of the two processes, the freeze drying and the spray drying. And so we use freeze drying a lot. So I work in natural systems, sediments, for example, and we use freeze drying to essentially allow us to gently break apart our sediment samples to be able to analyze them, extract them, etc. So you don't have to use a mortar and pestle and just beat the heck out of everything.
Yeah, okay.
But the question we always ask ourselves, and maybe you have the answer to this, is that how much does freeze drying change the morphology of the particles? You showed the two images of the freeze drying versus the spray drying, but I don't have an idea of what the particles may have looked like in suspension before the drying process. So which of the processes really, I guess, left much of the particle, the aggregates, integrity, versus which was more intrusive on the actual particle morphology, you know, which process? Can you comment on that at all?
Yeah, that's a good point. And I would be inclined to say that spray drying would give you more of that sense. Because spray drying would give you essentially, if you will, an encapsulation of the primary identities, right? Whereas freeze drying really functions to maintain macroscopic structure, right? So
Right.
if your material is, say, a cake or a paste or something like that, before you freeze dry it, it's going to come out as a cake or a paste, right? So in a macroscopic sense. Whereas if your material is, say, a solution of dissolved powder, then you'll freeze dry it and you'll most likely get a powder out as well. So even though macroscopic form may be maintained, I think if you have materials that are quite cohesive, as we see that skim milk can be, the individual particles you don't see post freeze drying, whereas you do see them in spray drying.
Oh, that's interesting. Okay. So I didn't know that. So that's a different take than I had in my mind. Okay. Thank you. And then the last. Go ahead. I'm sorry.
No, I was going to say that macroscopic structure is maintained, right? That macroscopic structure from the water scaffold is maintained.
Okay. Got you. Gotcha. The last comment was really more of an question, was more of an observation, and that is I was shocked by the difference in water vapor transmission between high density and low density polyethylene.
Mm-hmm.
You know, we use HTPE for most of our water sampling, not basing it on anything other than the fact that it's just high density. But so your graph of the water vapor transmission was really enlightening in that there's a pretty big difference between the two in terms of water vapor transmissibility and porosity. I didn't know that.
Yeah. Mm-hmm.
Yeah, thank you. Thank you. Any other questions, either from the attendees? Malcolm?
I actually did have a quick question. So we use freeze drying when we're done with the culture. We freeze dry it to maintain, just to get a snapshot of the ending biomass and toxicity, because I work with harmful species of cyanobacteria. And I was actually, the question is, when you freeze dry, does it change any of the characteristics of any carbohydrates or proteins? Because there are toxins that are both carbohydrates and proteins.
Yeah. And in terms of what type of characteristics?
Would they still be able to be, would it change the measurements on, say, a mass spec when trying to actually calculate concentrations?
Okay. I don't know the answer to that. I would say that freeze drying is very often used for biological systems because it has been shown to maintain viability and activity of biological systems due to the low temperature drying, particularly for materials that are zero tolerant, right? That don't do well with desiccating stresses or heat stresses or that kind of thing. But in terms of impact on some analytics like mass spec, I don't have an answer to that.
Thank you.
Keisha, I want to thank you very much on behalf of the Eastern North Carolina chapter of the American Chemical Society. It's an honor to have met you. It's really interesting to meet someone in industry, given I have my head firmly stuck in academia. And it's great that you're also helping and teaching as you can. And so I really appreciate your time. And Malcolm, thank you again for putting this together. And Ryan, thank you for organizing the event, the technology behind the event. And with that, Keisha.
I see one last question in the Q&A.
Okay.
And that question is, do you have any comments on the uses or possibly the misuses of cryoprotectants? Yes, I do have some comments on that. First, all cryoprotectants are not created equal. And just because something is a cryoprotectant in freeze drying doesn't mean it will be a protectant in some other process. I would also say that one of the key things that we often want to do in freeze drying is understand where glass transition occurs. And so some protectants, whether or not they are true cryoprotectants or not, some protectants may have glass transitions that are well above the temperature where you're going to freeze dry. So if you are still producing a rubber in your freeze dried cake, that may be to your detriment. Ideally, when we're freeze drying, you want to freeze dry below the glass transition of your material. So if your protectant has an anti-plastization effect or something like that, where again, it's increasing the glass transition temperature of the overall formulation, that will present some challenges in freeze drying.
Okay, thank you for catching that. Sorry, Chris, I didn't see you had an answer. I didn't see you had a question up there.
Well, thank you so much for the invitation. I really appreciate it.
Yeah, thank you again, and have a great evening. And let's keep our fingers crossed. We have lots of positive things to look forward to the rest of the year.
Thank
Thanks
you.
for giving the seminar. Appreciate it.
Yes,
so
thank you.
much.
Thank you.